Ok, buenas tardes a todos. Muchísimas gracias por estar aquí esta tarde con nosotros, escuchando esta ponencia que va a ser extraordinariamente interesante por lo que hemos podido hablar con el profesor Gudmundsson hasta este momento. Quiero también dar la bienvenida a las personas que están conectadas a través de streaming y, bueno, os animo a que después de esta charla hagáis las preguntas que consideréis oportunas. Le he pedido al profesor Gudmundsson que nos hable despacio para que todos podamos entender la conferencia, que será en un inglés estándar sin ningún problema. No obstante, yo voy a presentar al profesor en español, ya le he pedido permiso para presentarlo en español. Él me ha dicho que si preguntáis en español, él os responderá en islandés, con lo cual la comunicación será extraordinariamente fluida. Bueno, os comento que el profesor Gudmundsson es investigador titular de la Universidad Agrícola de Islandia, con la que, por cierto, tenemos convenio Erasmus. Una parte considerable de su actividad investigadora ha girado en las mediciones de los flujos de gases con efecto invernadero de diversos ecosistemas en Islandia y bajo distintas formas de manejo de suelo. El segundo centro de gravedad de su investigación ha estado relacionado con el inventario de emisiones de gases de efecto invernadero de la sección de uso de suelo, cambio de uso de suelo y silvicultura en Islandia. El acrónimo es LULUCT, es un trabajo que se está realizando a escala mundial para evaluar cuáles están siendo el impacto de los diferentes usos del suelo y sobre todo de los cambios de uso de suelo sobre la dinámica de los ecosistemas y sobre el calentamiento global. Vale. En principio, de su mano, y para apoyar la preparación de este inventario, se creó una base de datos geográfica nacional sobre el uso de suelo en Islandia, con el objetivo de recopilar datos disponibles sobre el uso del suelo, preparar los mapas de uso del suelo y estimar las emisiones de gases con efecto invernadero. Ante la escasez de datos sobre el carbono orgánico del suelo, en las distintas categorías de uso de suelo, se puso en marcha un amplio plan de muestreo de datos sobre el carbono orgánico edáfico y sobre la ocupación del suelo, cuya primera ronda completaron en Islandia en la década de 2007-2017. En esa prospección, uno de los principales expertos fue precisamente el profesor Gudmundsson. Dado que las emisiones totales son el producto de las emisiones por unidad de superficie y la superficie total, el perfeccionamiento de las estimaciones de esas superficies de las principales categorías de uso del suelo ha sido una de las partes más importantes de su actividad investigadora y de la que nos va a hablar en este momento. Así que, sin más, le doy la palabra. The floor is yours. Thank you very much, Professor Gudmundsson. Please be careful.
Yeah, hello. Thank you, Fernando, for the introduction, although I didn't understand a single word of it. So I'm not a Spanish speaker, but we will try to do this in English. And English is not my native language either, so we are meeting in the middle, so to say. And if you have any problem understanding, please, or if I speak too fast or too slow or not clear, please interrupt and do not hesitate. Okay. We have to find out the... yeah. I'd like to see the slides I'm presenting. So not good to turn it back into the slides. First, do you hear me? Yeah. It's okay on the online too. Okay. First, just a few words about the university where I come from. It's a quite small university. It was merged in 2005 from 3 institutions. It was an agricultural college on the west coast of Iceland, and it was an agricultural research institute where I was working before that. And it was also a school of horticultural Sciences or Horticulture in Hveragerði, which is a bit east of the capital area. And these schools were institutions, they were merged in 2005 and to the Agricultural University of Iceland, and it has been operating since then. It has two campuses, one in Reykjavik and one in Hvanneyri. The main subject is, as the name points to, agricultural science, but we have always been very active in the environmental sector. And also we include, oh, what did I do? Okay. There's also a faculty of planning and design included and there was horticultural science. What is disturbing us? Okay. Maybe I should leave this alone. And there's also a department which takes care of vocational training of farmers and advisors. So we have a broad perspective, but not very many students, but we try to do our best. And we are, taking care of the agricultural science in Iceland. This is roughly the structure of the university. We have 3 faculties: agricultural science, environmental and forest science, and the planning and design. And then we also have an interesting part here. We are part of the University of the United Nations for land restoration. So we have international students coming from mostly from Africa and from East Asia, from countries where there is a severe erosion ongoing and need for revegetation and restoring land. So we have a kind of specialized in that part of science, we would say. Okay. Myself, I'm a biologist, probably Fernando already told you. And these are some of the subjects I've been working on which are related to this presentation. And as it's often in small companies, small universities, you have to do a lot of things. You can't afford to specialize, oh, I only look at trees, and this, especially this tree, and only the roots, or whatever. But you have to do a lot of things, and it's a benefit in a way, because you learn to know the whole circle, so to say. And you have to do the field work yourself also and go all the way. You're just not sitting on a desk and in a desk on your office and writing papers, but you do make the applications and da-da-da-da-da. Okay. This presentation, I will start with a prologue, if you can call it that. Then we'll talk something about SOC, which is Soil Organic Carbon abbreviation, on its role and status and how we quantify it. And then I will tell you about 4 projects which I have been involved in or directed in some way. And that's it. And we can have discussion, and if you have questions on that. Okay. So you all know this, I hope. I think it's no question that in our days, and has been for too long time, the environment has been declining. We have global warming due to increase of carbon and other greenhouse gases in the atmosphere. We are losing soil, and we are losing the carbon from the remaining soil. We have intensification of use of resources. We have the wild nature declining. Natural environment is on the retreat, and we are losing habitats. There's a massive loss of biological diversity. There's an unprecedented rate of species extinction, and as a follow-up or as a consequence, we have increasing social unrest, and we have increasing inequality of people. So this is not a very bright vision. I wish it could be much more optimistic, but somehow I think we have to face this and do something. We can't ignore it. That's at least my opinion. One part of it is it's from the Framework Convention of, IPCC, what it stands for. It's the International Panel on Climate Change. And it regularly publishes reports on the situation regarding climate change. And I picked out some points from the chapter on land and land use. About 1/4 of the increase of carbon, annual increase of carbon in the atmosphere comes from land use and land use changes. It's not all about burning fossil fuel. There are also other components, and land use is one of the very important components. And land use is adding about 1.6 pegagrams per year to the atmosphere as CO2. And that's about, the 1/4 of the annual increase. With accumulated addition since the start of the industrial area, around 1650, land use has added about half of the amount that has been added because of burning of fossil fuel. So it's a, what did I do now? Okay. So it's half as important as fossil fuel. So we have to think about how we use the land. And one of the first things you learn in chemistry is the preservation of masses. Carbon doesn't disappear, and it does not come from nowhere. If carbon is added to the atmosphere, it comes from somewhere else, and it comes from the land. So addition to the atmosphere means loss in other places. And managed land in general is losing carbon. Then we have something that's called residual sink. So despite the managed land is losing as a whole, there is more carbon absorbed from the atmosphere to land than is released. So this is the residual sink. Okay, sorry about this. I should leave this here. And this residual sink, it's a kind of feedback by the land to the increased carbon dioxide in the atmosphere. As you know, you probably know a lot about greenhouses. And in greenhouses, you pump in, sometimes at least, I don't know the practice here, you pump in carbon dioxide to increase the growth of the plants. carbon dioxide is the food of the plants. They absorb it and turn it into glucose and other carbon components. Part of it is because of the nitrogen deposition on land, which is a fertilizer, increases the growth. And also there are some climate effect because the climate is warming, plants grow faster when they have longer seasons and things like that. And also part of this residual sink is because of regrowth of deforested land or afforestation. Have you read this book? You should. It's an interesting. It's a, yeah, as it says, it's a witness statement of this guy, Attenborough, and there are several chapters in the book. And every chapter he starts with 3 numbers. He starts with, this is the year in his lifespan. He starts with the human population, number on human population, how it was when he was born or about that, and how it has been increasing through his life. And the second number he is adding is the carbon dioxide, concentration of carbon dioxide in the atmosphere. And that has been increasing too. And then we have the third thing that he started, just 3 numbers in the beginning of every chapter. And that's the remaining part of wilderness. And that has been going down. Just in a lifespan of one person. So when you are 80 years old, if we are still here, probably this will go on. So it's your environment that you have to think about. This just in a lifespan of one person. It's not any person, but it's a very good book, and I recommend it. It's easy to read and you learn a lot. Yes, we are losing with the wild. There's a study paper by Ellis. This citation is from it. In 1700, half of the terrestrial biosphere, half of all the life on land, half of the area of the land was wild. 1700. Without any human settlements or any land use. Or most of the part that was in use was in what's called semi-natural state. Just slight land use, maybe some grazing, hunting, things like that. In the year 2000, things have turned around. With the maturity of the biosphere in agricultural and settled environments, as inhabited or cultivated land, half turned around. And less of the remaining part, 20% as semi-natural, and only 1/4, 25% remain as a wild. Okay. Don't get depressed. So what does it mean if we talk about carbon in soil? So the terrestrial ecosystems, they are compensating for the loss of carbon from the managed land through the residual land sink. And this residual land sink, it has been increasing. So they are, you could say, the remaining wild area is working harder and harder to absorb. But if you take it from the atmosphere viewpoint, then managed land is emitting CO2. And unmanaged land, semi-natural land, is absorbing CO2. And the area of this unmanaged land, the wild nature, is shrinking. So what are we doing? We are converting land from the absorbing category to the emitting category. Actually, we don't need that. Okay, you probably heard about these planetary boundaries. They are also going the wrong way. Here in 2009, that's not very long ago, the three boundaries crossed. The boundaries are the limit that of certain components that the planetary system is expected to tolerate. Things like climate warming, pollution, and things like that. 2015, 4 boundaries were crossed. 2023, 6 boundaries crossed. So it's not going the right way. We should try our best to convert this. And okay, we can add several, I'm not going to go to details to any of this, but we can add some more parameters of decline that we see in the environment. Here we have water in aquifers. This is from 1980 to 2020, it's a 40-year period. This goes down, this. So water, you're losing water from the aquifers. This is something called material footprint. It's about how much of material we use in the ecosystem, to our economy. It has been going up. We are consuming more and more, and it goes up with the growth in the economy. And also population is growing. So we recently reached some 100 billions of tons per year in material footprint. And chemicals and plastics are accumulating all over. So, okay. I think. And soil is also losing. So it's my point in telling you this. It's not to make you depressed, but the point is this loss of soil carbon is not an isolated issue. It goes along with other declines in the natural environment. And here are some numbers on the loss, the global magnitude of carbon in the soil. It's up to 1,500. It's in pegagrams. Yeah, that's the stock, estimated stock. Historical loss has been around 135 pegagrams, and the potential of soil to sequester. It's from this paper here, Digging Deeper, it's called, after Ratan Lal. And here we have the estimated potential of carbon sequestration. And if we compare it to the number I showed you before, how much land use is added, it's an interesting to see. This is about the same level. So we have a possibility to turn this emission from land into absorption by properly managing or leave soils alone to do the job. Okay? So this is my point. It's not an isolated issue. It's parallel to other indicators of nature decline, and I just want to say this is my opinion, and this is a result of our economic and social system. That's right. And I think it was in 1970 or something. There was a famous book in environmental science, Limits to Growth. Its point was maybe, okay, we are running out of all the resources. But we are pretty much getting the picture that was drawn up there. We have had the warning for 60 years almost, but we still have been increasing our material consumption. And we have been increasing the economy, consuming more and more and more without thinking, probably, a kind of automatic driving. So we must rethink and redesign our economy and how we treat nature if we have to survive. That's a sad case, I think. Okay. Soil organic carbon. That's the subject I should talk about. It has very important roles in soil. It's essential to the water holding capacity. The more of the carbon, the more the soil can hold and store of water. The water is, of course, necessary for plant and ecosystem to grow. It's also important for the soil texture, how the soil is built up, and how it sticks together for its cohesion. If it's too little of organic carbon in the soil gets loose and it's easily eroded, both by water and wind. And it is the substrate for the life, for microbes, the animal lives in the soil. It's the substrate. It's their food, and it increases the fertility. And it has been, so just citing this, if the concentration go below some critical limits, that depends on soil types and things like that, we are risking the soil just to collapse and getting lost. So it's a very important thing in soil. So same story actually, and it has the best. It's actually the best indicator of soil health. How much it can keep and how much soil carbon is in it. And it's very sensitive to how we manage the land. There's a growing interest because of climate change and see, okay, soil is capable of sequestering carbon, it can absorb. Okay, why don't we solve the problem by just sequestering carbon from the atmosphere to the soil? It's green, but to do this, okay, if we agree on that, we said probably don't. But we always need a good way to measure how much it is in one time and how it's changing and how it's responding to our management. So carbon sequestration to soil is often suggested as a mitigation, as a compensation for or decreasing the effects of other emissions. From burning fossil fuel and it is in a way it's sold as an absolution or letter of indulgence as the Pope presented many years ago. You could buy a letter that released you from your sins. And you often hear, okay, this is carbon neutral, we do this and that, so you can keep, it's okay to buy this, it's carbon neutral. So we have planted some trees or put some carbon into the soil, so okay, don't worry. Just buy more. But why is soil capable of doing that? In normal situation, it's a stable ecosystem that has been evolving, a natural ecosystem, the soil has about the same level of organic carbon all the time. It's just going in circles, it's not increasing and not decreasing, it's stable. But soil is capable, in many areas, is capable of absorbing additional carbon, and it's mainly because it has lost so much. It should be much higher level, but it isn't, so okay, we can add to it from the atmosphere, that's a good thing. If we add more carbon, we improve the soil health. And that's a very good thing to do that. But in my opinion, we should concentrate on improving the soil for the soil itself, not to use soil as an excuse for emitting more in other sectors. We should not burn more oil or say, okay, soil takes care of it. But the soil needs itself for its health, so that should be the issue, not as a scapegoat for keeping on consumption and burning fossil fuels. There are many, say, scales regarding measurements of soil organic carbon, and you can be working on any of them. It can be you can be just looking at the field scale, how much carbon is in a particular field, and the farmer probably has just have to take soil to his hands and he get a feeling of how much it contains. He doesn't need any exact measurements. He knows his soil is in good health and keeps on doing things the way he has been doing. But you can also be worried or need to have an estimation of soil organic carbon on a regional scale, or you can also concentrate on a management category. How is cultivation of particular plant, treating the soil, should we change, or what are we doing right or what are we doing wrong, things like that. So you have also different purposes. This is probably this is the beauty of it. So but then we have also national inventory, things that I have been working in, and we have, let's say, the market looking for mitigation option. How can you sell us some land or take care of some carbon for us? And okay, we'll pay you something, and you guarantee you put it in the soil, and we can keep on our business. And we have a carbon market. And in that, if you are here, then you need probably more verification of that you actually have accumulated the carbon into the soil. Methods. This is a nice picture which I picked from the internet. Here we have, say, the very primary status, no vegetation on soil, and just it could be a, if I take an Icelandic example, it could be a land that appears when the glaciers are retreating. Then as time goes, maybe thousands of years, soil builds up slowly and slowly, and probably it reaches a state of mature or fully, full-grown ecosystem, and then you have just acquired some status and you reach some equilibrium level. To measure this, to measure soil changes in this carbon, we need samples. That's one way to do it, so say. And we take samples here in certain management, and then after maybe 10 years, or depending on how fast the system is growing, or how exact we can be in our measurement, and if we have still, after 10 years or 15 or 50 years, we still have the same management, we can say something about how was this management treating the soil. We could also have changed the management, and we can see the effect of this management changing. This is one method. Take samples at different times. And sometimes you can also exchange time with space. If you're looking at the management, and you have had management in 10 years here, and here on the other side, beside it, you can have management for, same management for 20 years and things like that. Then you can, in a way, you can exchange time with space. And then analyzing the samples, there are also different methods in analyzing samples. Some of them are high-tech, some of them are old and low-tech, so to say. One is this is probably mostly done in scientific studies to have the dry combustion, and it gives you the ratio of carbon per gram in soil in the dry matter. And then you can have simply the loss of ignition. It returns the organic matter. It's not exactly, it's almost double the amount of carbon, but in some cases that's all you need. So it's and you have other methods more. Some of them are very old and well known as a titration method, or you have other methods, and it's a constant development of methods to try to get things simple or faster or take larger areas. But you should always consider why am I doing this measurement, and what do I need, and how exact and expensive can it be. Then we have a different method to estimate changes in soil carbon in some place, and that is to measure then we look at the soil as a black box in a way, and you measure the fluxes that come in from the atmosphere and those who go out. And you say, okay, difference in what comes in and what goes out has been stored in the soil, so it has increased there. The same should be approximately the same amount. But just things are in reality are probably a little bit more complicated, but not necessarily depending on the accuracy you are requesting. And we have sometimes other outputs or inputs. You can have organic fertilizers, or you can have harvest moved from the soil and things like that. Or you may have some organic matter flowing away with the water. But that's, yes, depends on how detailed you want to be. And these are the two methods very often used. This is what we call chamber measurements. Then we put the chamber on the ground. You see it, we have a frame here, so it's closed. It's air don't come out or don't go in, so it's okay. And we measure the concentration of CO2 inside over time. So we see an increase or decrease. And usually, if we are interested in both fluxes in and out, we measure it in ambient light, and then we put some cover over the chamber, and then we stop the photosynthesis, and we have the respiration. And this is called an eddy tower. And this is continuous measurements of carbon going up or carbon going down. It's a high-tech and expensive instrument, and you can run it automatically over a long period. It's probably not much going on there at the moment. In this situation, this was taken where we were measuring fluxes from a hydropower reservoir. We had some program there. Okay. Before project, I'm going to tell you a little bit more about project I have been involved in some way. One is connected to the countrywide estimation of carbon and monitoring, trying to monitor it. We only did the startup phase of it. And then we have a project which was a management effect. We were comparing grazed area to areas where grazing had been excluded. And then we had a management effect, a project called Carbon Par. It was on golf courses, and as a part of that, we designing a kind of carbon scoring system. If you play golf, which I don't, there's a certain scoring system, and if you depends on how accurate you are in bringing the ball to the hole and how many shots you have. So it's a analogy between the scoring system of the courses and the players. And then a project about drained wetlands, carbon fluxes from drained wetlands. Okay. In my past, I was responsible for combining or compiling the data for the land use part of the inventory of greenhouse gases to the Climate Convention. And this project was established because we had there was a lack of information about how much carbon do we have in the land and where is it. So we started this project, which also had some other objective on mapping the land use. And but the main object was to obtain a countrywide information on soil carbon. And also to explore the relation of soil organic carbon to land cover classes, to vegetation, erosion, and other topographic features like slopeness and altitude and things like that. And also establish a baseline for further sampling. We started field work in 2007 and finished in 2017, and this project was financed by the Icelandic government. This is a situation that we have been dealing with in Iceland. You see it. This here, it's barren ground. No vegetation, mostly no carbon in the soil, probably small. But here we have some remains of the land as it was before. So we lost the soil from here, and thereby we lost the carbon also. And of course it goes somewhere. It doesn't disappear totally. So it has been estimated that about half of it was emitted to the atmosphere. This is something also about the situation in Iceland. We have here different land types. We have the erosion is one of the bigger environmental problems in Iceland. We have most of our soil are what is called volcanic soils. It's andosol, and they are very vulnerable to erosion, especially if the carbon stock goes down. The vegetation opens up, and it's very vulnerable to wind and water erosion. And through that, probably in 150 to 200 years, we have lost large areas of vegetated land. So that's something that we are not proud of, but this is what happened. People didn't know it. One cause could be, okay, the climate played a part in it. We had a cold period, and it was also, as many have pointed out, it was also one of the consequences of overgrazing. So we don't have large area of the same soil or same vegetation, so we have very small pattern. Well, that's okay. We couldn't go to every single spot, so we had to find a way to sample this. And what we did in this project, we kind of laid a grid or a fish net over the country, and we started first. Okay, we just spread random points and picked from that. Okay, that should take care of the statistics and things like that. So but that took far too much time to walk to one point, maybe 3 or 4 hours, because it's far away from the roads, and that didn't work. So we made clusters. We have tell you about how they are, and distributed them on this grid net. And we had 2 kinds of clusters. It's not the green and the blue, but they are these here in the highlands. Then we had this more homogeneous land. It's less vegetation. It's probably subjected to less vulnerability. Some of these points here are up on the glaciers, and we didn't go there. But we had a less effort in the highlands. But on the lowland, which is mainly where the main land use, we had more effort. And these clusters, they had 2 lines with 2.5 kilometers in between and 10 points with 500 meters in between. Well, it's a kind of preset points where we did go to just with the GPS, and we walked to the point, okay, here I am, take sample, look around. And there were 2 grids on that. Can you guess what is going on here? This is a hydropower reservoir. So the water line goes up to here. And all the vegetation, which was just similar to what we have here, it's like this. We just drowned the vegetation over there. So, but it remains, and some of the soil is still there, expiring, but there's nothing renewed. Okay. The objective by the field champion was to check the land use map and how accurate that was, and obtain data on relative size of land use categories. Because at the point we recorded, okay, what type of land is that? And obtain data on carbon stock in various land use categories, and you would say a kind of, not say a dream, but the ultimate goal to be able to present a carbon map of Iceland. And have some data for land condition and management category and grazing intensity. We try to do that. But yeah, sampling area. That was also. It's not. We walked to the point that the GPS told us. Put a stick, and our area, observation area, was a circle of 3 meters. Okay, we could do it larger, more time, bigger, more variability and things like that. And then inside this circle we had 3 smaller frames which we checked the vegetation more and did some sampling in there also. It's very nice. It was a pleasure to work in this project, to have the privilege to go up to look at your country through this way. So if you want to have a nice holiday, take some GIS maps or put random points and say, okay, I go there. You don't know what it is there, and it's an adventure. So maybe we should start a tourist business doing this. Okay. Go to this point and take a photo. So we are above the clouds there. And this is the circle there. And at each point we estimated or measured several categories: vegetation, erosion spots, hummocks, and landgrass, and things like that. Looked for grazing mats. We measured soil depth and some index plants, and we had some plants that we knew that were preferred grazing plants, and others that were less preferred grazing plants. So we could get a kind of estimate of how intensive the grazing was in the area. And we took photographs of every point. And after 5 years of working, we added some variable. Okay, we are probably not doing good enough on this parameter, so we added and changed added some parameters. like the activity of the erosion, was it stable or was it ongoing, increasing, or were the erosion spots healing? And some more data on why we estimated the intensity, or why we estimated this area grazing. Did you see foot marks, or did we see marks on the plant that have been bitten, or and we added additional sampling also. And in there we sampled soil, and we did it just by taking soil cores from 0 to 30 centimeter depth, and we took 5 randomly within the circle and just pulled them together. So that's a kind, instead of taking 5 samples, spending money on measuring each of them, we just pulled them and measured one. So that's a kind of average of all the samples. Yeah. And inside these we had total vegetation cover and some groups, we would call it ecotypes. So we estimated the coverage of each of the category within the frame, and we had 3 of these frames. 2 of them were at fixed place, and 1 was just random. And we used, 1 meter downwind from the stick, in the center of the circle. And photograph of each frame, a lot of photos. And we sampled above ground biomass to have, there are 2 storages in the land. It's the soil and it's the biomass which is above ground. This is not an ideal method to measure stock of soil organic carbon. We miss some parameters here. But we had a kind of compromise with that. We should, if we are going to get the stock, we should also have measured the bulk density and also the coarse fragment ratio, and then we could calculate the stock in land to a certain depth. But time-saving compromise, we had about 2,000 points to go to, and there were not many people, mostly 2 at the time, so it was a lot of job, and we'd say 1 line in 1 cluster was 1 day work. Sometimes you had to walk for maybe 10, 20 kilometers to the first point, and then sample on the way back. So we had to do some compromises. And the data processing, it's say that's work in progress. We have measured all our samples, and we are just beginning of working with this, correlating the carbon to the other things we measured, and also how can we interpolate or create models to predict the carbon in other places that we didn't visit. We have here what is called the farmland database. Then we have a 10 land cover category. They were obtained by remote sensing from pictures from satellites which were classified, and then the people went out to random points to check the classification, and the objective was to, I think, 70% correct, reach about that. And in most categories that was obtained. There are some categories that were very difficult to get the correct classification. And in this project we recorded, then we had additional kind of I think because it was random, we could also use that as a check for the total value of each category. Okay. In my mind, there are many possibilities of working with this data. We could use vegetation cover, ecotypes, and index species to correlate with the carbon. We could also supplement this with the grazing intensity or pressure, or build an interpolarization between categories, but then we need to have the data to use for the interpolarization. And something published, you just say this is an overview summary of what data we have. And there was also an MS thesis in statistics last year. That was a guy who was trying to fit a Bayesian model to the carbon concentration measured and try to see if the model could identify the most important parameters that control the carbon content. It was an MS thesis, and okay, some of it returned hints, or it's not, the problem is not solved, but it's a good start, I would say. So we had and there are more options to work further on the data. And I think the data, we have about 2,000 points. We have a lot of other data that can be correlated, and it means also 2,000 soil samples and samples from the above ground vegetation and things like that. And it's an opportunity, I think. Okay, what did I do now? Yeah. You could use it as a subject. It's available if someone is interested to get access to some of this data and do something with it. Just on normal terms, we get the benefit of the data processing, and you get something to work on. It could also be job opportunities for postdocs. We don't have the money yet, but that's usually not the core problem. We can apply for grants for doing that, and I think we have, since the data is already there, and there could be opportunities to play with this data, and you could also get some spin-off studies to, okay, we didn't have not enough data or knowledge on this component, and you could get some spin-off on that. So, okay, you're welcome. Who wants to come? No one. This is a second example. This is a management study, and it's about grazing. It was a project financed by the Norwegian Council of Research, and Anna Guðrún Þórhallsdóttir at the University at Hólar was the leader of this project. And we compared, in this project, we compared soil organic carbon, CO2 fluxes, and greenness, NDFI. I don't know if you're familiar with that. It stands for normalized differential vegetation index. And it measures the amount of chlorophyll you have on certain area. It's widely used in environmental science. And you can both take pictures or measure it on the ground, or use satellite images to get as I said, we compared areas that were comparable in all other ways except this one factor of the grazing. In Iceland, there was around 1950 or something like that. There was it was common that on farms you fenced in some area and planted some trees. It's not big area, probably 50 meters squares or something like that. But many of these areas, they have remained within fences for 40 to 60 years. That means that grazing was excluded from this area. But just on the other side of the fence, the grazing kept on as before. So this was the area, two areas that we compared. And we managed to publish a paper about that. And the main findings, the sea stock, the soil organic carbon stock in the grazed area was larger than in the areas where grazing had been excluded. Probably not as expected because, okay, grazing is taking away the carbon from the system, it goes somewhere else, so you should be losing. But plants, especially grasses, they respond to grazing by growing faster, and you increase the circulation of nutrients by grazing. They digest the plants and return nutrient-richer material on the ground than the grasses were, more concentrated nutrients on the ground through the fitches. And we also saw this in the fluxes, the CO2 fluxes. They were larger in the grazed areas. And the grazed area were also greener. Okay, here we have it's not a whole year study. We did not have the year budget, but we measured all the sites at the same time, so to say, from one to the next and next. So we have similar conditions, same time of year, same days. And this is area where we had intensive grazing, very intensive grazing sometimes, and then extensive grazing. That's a kind of grazing management that is very common in Iceland. You just open the gates in the spring and you release the sheep, and they go around in large area and graze freely. It's a kind of extensive grazing, and then this area, no grazing. See these fluxes, these are three parameters that we are on these graphs. It's the NEE, which is the net ecosystem exchange, that's the difference between the respiration and the photosynthesis. And then we have the photosynthesis and the respiration. So these are quite similar, but in the area where there's no grazing, much less fluxes. And we measured the fluxes with chambers, as I told you before, how that is operated. And just the average of all the dates for each site. See again the difference. The photosynthesis is much larger here than on this area. The respiration, that's this one. It's also larger here, but the net exchange is larger in the grazed area than it is in the areas where we had excluded the grazing. So, okay, if you come, it's just it's probably not, if you think it in a simple way, okay, grazing is removing something from the system, it's not good. But the system, the response of the system, the ecosystem is in that way that it increases the photosynthesis of the system, produce more if it is grazed. It's kind of logical. If you think of it in evolutionary terms, an animal that would degrade the system and survive on would not have any change. So it's yeah, in that way. But I didn't think that way before. So I'm not always logic. And this is the greenness. It was, yeah, not statistically significant between this intensive and extensive, but when it comes to the no grazing, there was a statistically significant difference. And the soil carbon. The soil carbon was larger in the grazed areas than in the ungrazed, or in the grazing have been excluded. So my view on this, how to explain, if you have a larger input, if you think of it as a barrel of water, and you have water coming out, and you have some pipes going out also. And if you increase the flow in, but keep the flow out, in a way, you increase the level. So it's a kind of, yeah, physically logical in a way. So it's because you, and if you stop grazing, that's what happened here. You stop grazing, then the system starts losing carbon. So grazing is according to this. Okay, other studies might disagree. According to this, grazing is an important factor to keep a higher level of soil organic carbon. Keep up a higher level of soil organic carbon. If you stop grazing, you can expect the level to go down. Yeah, these are okay. I'm ahead of myself. Okay, this was the kind of summary. We can let it stand here. So it was interesting, and there is a follow-up on this going on. Taking this, we only had 5 areas in each category. That's not a lot, but it showed us the trend, and now we have a PhD student which has much larger sampling and looking at more components and things like that, and hopefully he will finish soon and start publishing paper on this and on the subject. I think it's interesting. What we did in this to measure the stock. The carbon content is measured usually in the particles that are less than 2 millimeters in diameter. In this project, we sampled the bulk density, and we also measured the coarse fragment ratio. That's the ratio, the volumetric ratio of all the particles that are larger than 2 millimeters. And we, show you it. And if we have all these components, we can calculate gram carbon per cubic centimeter or whatever unit you use of soil. And if you add the thickness layer you are sampling, you can have gram carbon per area. one thing that we were dealing with, how should we approach this? And how should we divide the soil to different layers? There's many options to do it. It is if you were a soil scientist, which I'm not, you would have a kind of pedagogic approach. This is this type of layer and this type of layer and da. I even don't know all the classes they use. And then they would sample randomly from each horizon of the layer. But you can also use the pedagogic approach, but sample in a depth continuum. You don't sample just randomly in the horizon, but you take the whole column of soil and separate it into this horizon. You could also approach it, okay, I'm just look at the fixed depth layers, 10 to 20, 0 to 10, 10 to 20. This is actually what we do when we sample by soil cores. When we take 0 to 30, one sample. And this is kind of what we ended with. You take the profile and then you look at the profile and you see, okay, what we are after is this soil organic carbon stock. So if one of these parameters you need for calculating the stock looked different, if it was more stony layer, or if it was more dense layer, or if it looked as it had more carbon, probably color a good indicator, and you can feel it also in the soil, how rich it is with carbon, then you made a different, separate layer. So the objective was to get the amount of carbon per area. And then you can subdivide according to this. This is what we ended with in this. There we have it. Describe the profile, and then we estimated the core fragment ratio. And you can't identify visually just all particles that are larger than 2 millimeters. So most of the particles that are, say, between 2 millimeters and 2 or 3 centimeters in diameter, they come with the bulk density samples, and then you can sieve it and separate it to particles. But you don't include the larger stones in the soil sample. That has to be estimated visually. I don't know how clear it is. It's a profile. This is actually from Norway. We had a similar project there. Measure and then you describe and picture. See, there are some layers here, different here, and down there. And this is what I meant by sampling in continuum. This is where we sampled. Took all the soil from the surface down to the bottom of the profile. Or we used down to 60 centimeters. Or less if you were already down to rocks. Okay, see here. Okay. See here there are a lot of stone. And this you can estimate this. Okay, you can put some frames on it with a smaller grid, or just estimate it visually how large proportion are these stones of the layer we are looking at, and you just write it down. And it's a rough estimate. But the area is, we use the area to estimate the volume. If you had different cut of the profile, you would probably get different stone, but say that if it is 20% area of some square feet or something, is stones larger than 3 centimeters. What did I do? Okay. Okay. Bulk density. Bulk density, I don't know if you already know this and have practice in it. The bulk density is basically about getting a known volume of soil. And there are also different methods there. And when you have a sample, you dry it and separate to particle size categories. And you measure the carbon and other chemical components in the particles less than 2 millimeters. So you have to know how much how much volume do these particles take that you are measuring in. There are different approaches in this, depending on the soil you're dealing with. Why isn't it? Oh, okay. Okay. We have a cylinder put into the definite layer, and like this. And then you put a plate on it, and you simply knock it slowly into the soil, and then you excavate the cylinder. And here is another method. It's not easy to deal with this kind of rocky or stony surface. How do you measure the volume of the soil you excavate? What we did in this project is a different project. We had some rings here, put it on the place where we were going to sample, and then we put plastic bags into it and filled it with water, and we measured the volume we put in. And then we excavated the soil to the depth we wanted to excavate and measured the volume again. Then we have the volume that we took from of our sample. So, and this was in a different project. Sorry for just looping. Just a loop. This was on a project where we were trying to estimate how much segregation potential could be included in revegetation in Iceland to revegetate the land, the areas where the soil had been lost. And there's a paper on this published 2000, I remember, And we also described this bulk density method in a note. Okay, in the Climate Land project, we did a test just to show you. We measured on the samples. We measured both carbon with the dry combustion, and we also took the same samples and measured the organic matter by loss of ignition. And it's a very good correlation between these two components, and it's the same soils are compared. And there's a lot of money to save by just doing this. So it's important to consider what do you need. You can use this, just divide if you want an approximate carbon, but to measure the organic matter, it's half of the organic matter is carbon. So don't make it more expensive than you need. The third example, it's the golf courses. This is a private company that approached us, a guy named Edwin Rowland, and this was a project called Carbon Par, and the objective was to promote climate-friendly design and management of golf courses. The golf courses probably they don't have a very good reputation environmentally, so they have a case to defend, so to say. And the idea was, okay, design a scoring system for the golf courses, so kind of telling, okay, how much is your golf course scoring? And the objective of that is to promote improvement of land management. So here you have some information about the project. And here we started decided to start just on a rough scale. The fine-tuning comes later. And we sampled all the 60 golf courses in Iceland, few samples on each. And part of the project was also to map them. And basically here, part of it was, okay, mineral fairway or mineral rough. That's some difference in management. It didn't show up to make any difference. But in many of the golf courses, you have organic soils. And ditches in it, some cases this is former hayfields. And this organic soil is losing a lot. So this golf course, which has about, what you call it, three paths, or it has a lot of organic area that should have been avoided. You get what do they call it in golf? You get a bogey. If you play too many shots for bogey or something like that, or you get a bird and an eagle if you do a bogey if you are doing badly. So they this course get a lot of bogeys for its design actually. And we sampled soil cores, bulk density samples, and we did not dig profiles, but we used the bulk density samples to estimate the coarse fragments. And there's a collaborator, Maria Svavisdóttir, in this with me, and the guy who owns the project. In the scoring system that we are, say in a way we are preparing and estimating. It's not published, but we divide it to two categories. We take the mineral soils, and then we have a reference land, and we take the first project I told you about, where we sampled all around, and we estimate the reference soil for each area of the golf course, and take the sample there with the bulk density and the coarse fragment ratio, and instead of the measured carbon in the sample, we just add in the equation the reference value of the category. And then we can see, okay, is the golf course, or this area of the golf course, is it with more carbon than the reference land, or is it with less? That's so it's a kind of, yeah, let's say it's a beginning. And this guy who owns the project, he's a golf designer, and he has a connection into the golf environment in Iceland and abroad also. And he has been, yeah, he's very good at promoting things. And they had got the golf guys interested in, okay, we probably don't have such a good reputation. We should do something to improve it. At least, okay, we are, one of the benefits could be, okay, let's avoid using drained wetlands for golf courses. That could be one obvious way to improve your score. And the last example, that's in all these 3 projects we have taken soil samples, but there is a different method to measure the changes in stock, and that's especially when you, as in wetlands, you have probably soil that is, yeah, up to 10 meters, from 1 to 10 meters thick. It's almost, yeah, most of it is carbon. So, and when you drain probably the top 60 centimeters or something like that, and you have a shrinkage of the soil. So, and both because it loses the water and also the carbon. The carbon is lost from organic soil, just as a proxy or as a rule of thumb. It's about 0.5 to 1 centimeter per year that is lost, just emitted to the air from drained organic soil. So it's not very good approach to, okay, try to estimate the stock and come some years later and do another sampling. We would not see the difference because it's such a small change compared to the whole stock. So the method is to look at it as a black box and measure the fluxes in and out. And that's what we did in this. Yeah, this is a loop in the presentation. And in Iceland we have some tephra layers, volcanic ash, that are shattered or only when the eruption goes on. You have tephra going over large areas, and it leaves a kind of time mark in the soil. And if you know from which eruption this, for example, this layer came, you can say, okay, all the soil here above is from the period from here, when the eruption was, and up till now. And it was a project in MS thesis in Iceland that tried to estimate and it agreed with our, yeah, more or less with our research by measuring the fluxes, to try to measure, okay, we have a layer of tephra here, and compared wet soils have not been drained, and only close to it, compared drained side. And okay, what is the difference in stock? You have time layers, time stamps in soils in Iceland and probably in other volcanic areas too. And not probably, you have it. So that can be done. So you can use the soil sampling approach for wetlands. So if you have such time marks in the soil. But flux measurement in this project was chamber again. And we measured the net acoustic change and the respiration by darkening the chamber, putting them in dark, and you calculate the photosynthesis as the difference. And then we also had on the sides, we measured the variables that are kind of driving variables for each of the processes. The photosynthesis is mostly driven by PAR, which is photosynthetic active radiation, the energy source of the plants, and the amount of the plant or the greenness. And the respiration is mostly driven by the temperature of the soil. And we model this to find the annual budget of these areas. And this is the comparison of this is the photosynthesis. The red one are calculated, the black one are measured. And here we have the line, the model line for the respiration, and we have the measured on same days. And what we got out of it was on average for a 3 year, we did simulate for over 3 years of fluxes, and we got this number here. It is in tons share per hectare per year. And this number it's fluctuating. The most fluctuating is because we had a warm winter there, and the soil didn't even freeze all the winter, which it usually does. So there's a huge difference in respiration, and then we had much more net emission. But this number is quite close to the IPCC default value, or which is represented by the estimate of the. Okay, and the summary. The soil is not isolated in the system, it's part of other problems, it's not isolated and it's part of it. It's part of the natural crisis which humans are largely responsible for, or mostly. It's lost because of unsustainable land use. And we are converting wild areas which could be helping us with taking the carbon back. We are converting them to managed lands which are losing. And my opinion, we should be restoring carbon to the soil, for the soil, for restoring its health, not as an escape for good for other greenhouse gas emitters. And it's essential to measure the carbon at some time points to see what the management or land use is doing. And you should always, it's not one standard method that you use always. Adapt the method to the accuracy you need, to the money you have, and things like that. It's okay to start, if you don't know anything about something, you can start rough. You say, okay, this looks like it. Okay, let's sample in that way. And it's very important, in my mind, to use georeference sampling points. So you can sample other data without having, when you sample, I didn't know the altitude where the sample was. So you can find out by having the georeference point, having the GPS point, and then you can also get average temperature, slopeness, precipitation, and all the things. So you can add a lot if you have georeference points. Okay. This is what just a normal day in the field. Just a normal day.
Thank you very much, John, for your interesting presentation. And we have the opportunity to make some questions to our speaker. And if you have any question and you prefer to speak in Spanish, do it, and maybe I can reformulate your question into English for our speakers. Do you have any question? No? I have one. I have one for you. Yeah.
Okay, okay.
Okay.
Yeah.
Ah, okay. Hay una.
Thank you very much. ¿Dónde está mi pregunta? Okay, vale. What equipment do you use to measure CO2 flows?
Speak a bit louder.
What kind of equipment do you use when you measure the flux of CO2? In the chamber, outside,
Yeah.
in the soil?
What kind of equipment?
Yeah.
Yeah, we use, it's called IRCA.
Ilka.
Yeah.
Yeah.
It's based on, it's actually the same principle as global warming.
Okay.
You send a radiation of near-infrared radiation through the sample, and the CO2 absorbs a certain amount of the radiation, and the instrument calculates the difference and converts it to the concentration of CO2 in the sample.
Okay. Thanks. Yeah. Thank you.
There is a question, I'm sorry, so loud. There is a question online also. I'm going to try to translate. It's something like how we can achieve sustainability in nature in relation to soil carbon and also in relation to environmental pollution. It's a huge question, I think.
It's a little bit big question. Very big question. Maybe short answer should behave. But yeah, how can you achieve sustainability in soil? You have to, first you have to know what effect your management has on the soil. And if it is unsustainable, then you have to find ways to change your management of the soils. It can differ. It's not always obvious, as I showed you with grazing. Grazing, maybe I'm probably not with the correct image in my head, but before I thought, okay, grazing, just kind of logic, it removes from the system, and you should, as a result, it should be less in the system. But it speeds up the system. So you have to measure and have control of what you're doing. I think the first step would be to have the objective of sustainable use. Then you are decided to go that path. And it's not that I know at least no simple answer to how you do it, but you should strive to improve things. And it will take time, of course, but some things are well known, like draining of organic soil, it's not sustainable, and overgrazing is not sustainable. Too intensive can harm the soil, and things like that. So, try to modify. There are different schools. Some say, organic farming, that's one way. I don't know much about that. But you should be aware of where you're trying to go and learn by experience.
Thank you very
No more question? Yes, my turn.
Yeah, okay.
Okay. Well, I agree with you that the prospective field sampling studies are very interesting because we need some data about soil organic carbon, but currently in Europe there is a tendency to study the carbon stocks using near infrared spectroscopy techniques. So, what's your opinion on these techniques?
Yeah. I've I've mostly heard about it, but we had some years ago. I was involved in a project where near infrared spectrometry, was used to analyze different fragments of carbon in plant residues, and that worked very well there. But there are some additional problems in soil because you have all the other particles. You might have to some way extract the carbon, and then you can standardize the method. But in some basic component in the NIR doesn't measure a quantity. It basically, as I understand it, it's a comparison of samples. Mm-hmm. So you need to have a good database behind the measurements to refer to, okay, you have a good database of near reflection of certain soil types, and you take a sample, okay, you measure the near reflection, okay, this fits in here, and you have on the database, you know how much carbon is according to this spectrum. So but you need a good database behind it to be accurate.
So this is important, the field perspective method. Okay, thank you very much. Any other question? No? Yes. Yeah.
You have talked about the carbon market. Yeah. And how many will cost, I don't know, 1 ton of carbon to adit to the soil, and how come the companies would pay for that?
May I be very honest? I think this carbon market is a way of a bullshit. It's we have in Kyoto, there was an agreement on climate convention, and unfortunately, that discussion was persuaded into the channel of, okay, the market can solve this, the market can solve this. But we have now about 30 years, and the problem has just been increasing. You can't solve the problem by the same methods that created it. So the prices, and the company that buys it, okay, it may work for the company, for the account, green account of the company, that's okay. You get a better image, but in the end it is to sell more, produce more, which is actually working against the objective of sequestration. Does that answer your question?
Okay. But any other question? No? Thank you again, John.
Yeah,
it's good.
You. It was a pleasure.
A pleasure for us. Thank you very much. I'm going to speak in Spanish, just for a little.
Yeah.
Okay. Gracias por haber venido a todos, gracias por vuestra atención, gracias por haber estado presentes y con respeto. Os recuerdo a los que os toca que el lunes por la mañana tenemos un seminario en el invernadero sobre lucha biológica, ¿de acuerdo? Venid los que podáis, ¿de acuerdo? Muchísimas gracias de nuevo.
Los estudiantes de doctorado, por favor, no vayáis sin firmar la lista de asistencia, que no sé por dónde anda.